Shall we start? Sanjay?
Yes, sir. Yes.
Okay, thank you. Who's today? Abhishek, pilotless target aircraft. Correct?
Yes.
Abhishek, are you ready?
Yes, sir.
Yeah, you can start sharing your screen.
Can you see me?
Yeah, yeah. Just the voice is a bit less. You can talk a bit louder.
Okay. Okay. From Group 2, I'm here to present about wing-loading estimation. The topic given to us was pilotless target aircraft, and this is our group members. Media, Ganesh and Varush Prakash. Starting from requirements, the range given to us was 90 kilometers, endurance is 50 kilometers, 50 minutes.
50 minutes, right? 50 minutes.
50 minutes, and maximum speed is Mach 3.8. Payload is 40 kilometers, and it is used for missile development. As you can see in the image given in the right side, we will be having pneumatic takeoff, climb, acceleration, combat, and parachute recovery system. So we will be seeing wing loading for this mission profile, except for parachute recovery system. Equations that we have used for takeoff, as we took from the equation in Thomas group, takeoff velocity should be 1.2 times of Vs, but from literature study we got to know that for pneumatic object it should be 15% more than the external. So we slightly modify the equation, and rest equations are same. We took it from Thomas law.
Did you use the same mission profile for weight estimation also?
Yes, sir.
Okay. So no takeoff, no fuel is consumed there.
No fuel. Yes.
Okay, yeah. Continue.
And these are the equations that we use for acceleration, combat, and service.
No, go back. I want to see LT. Actually, for combat and both insert and external sustained turn, you can just use some nice value of n. That's good enough. So for acceleration and combat, one value of n will cover everything.
Yes, sir. We used 5, sir, for load factor.
5. Okay.
Yes, sir.
So that's enough. You don't have to do all these things.
Okay.
Yeah, go ahead.
So the assumption we took, aspect ratio is 1.5, maximum serial max 1.1, coefficient of zero defect 0.05, Oswald's coefficient is 0.31.
E seems to be very less. Why?
Which one is less, sir?
Oswald's efficiency factor.
Yes, sir. First we actually thought like that mainly, but we took it from reference aircraft. So
Because I think it should be at least 0.8, if I'm not wrong.
it is in at supersonic, sir.
Supersonic. Okay. Yeah.
Yeah. Rate of climb is 25 meters per second. Our cruise ceiling was 15 kilometers, and this is the initial assumption we took for the cruise ceiling, and NS5. As you can see, we varied our ceiling altitude and got the ceiling condition for wing loading for the ceiling condition. And
what velocity did you take for this? What ceiling velocity did you assume? Oh, no. It should be different from here. Slightly different.
Yes, sir. The velocity will slightly change. Initially, it will be 1303, but since the altitude is very high, it will change to 1121.
Okay. So you assume the same Mach number, but then Mach number. Okay.
But velocity will change. But we consider that. And we found out that 30 kilometers was our a perfect altitude, perfect sailing altitude, and these are the graphs that we got from sustained turn rates.
Yeah. Continue.
And one second. In instantaneous turn, we actually got only the turn rate and wing loading graph. We have been slightly stuck in that. We didn't get that thrust to weight ratio and wing loading graph. So
I'm telling you, it's not necessary.
Instantaneous turn.
Yeah. That's why I'm telling. For every turn, sustained turn, just assume n is equal to 5 and draw the graph. That's good enough. Okay. Yeah. That's what I told earlier.
Constant graph. Since we thought we should add that, so we didn't combat. So without combat, this is a graph for climb, takeoff, acceleration.
Okay. For anyway, I will leave the question to others. That's all. That's all. You have something more.
Yes, sir.
Okay. I leave the questioning. After that, I will give the comment. What is the earlier slide you showed? One slide later.
And things that are to be done. Meaning the combat field.
I'll give my comments, but let others ask the question this time. Then after that, I'll give the comment. So, any questions?
Sir.
Who is it? Sanjay.
Sir, Sanjeev. Sanjeev.
Huh? Sanjeev later. First Sanjay, then Sanjeev.
No, sir. Sanjeev raised his hand first, so he can ask.
Again? Okay. Whatever. Yeah. Sanjeev first. Yeah.
Abhishek, can you show your constant diagram? So, can I ask why the climb graph is a perfect straight line?
That's exactly what I wanted to ask, but good I didn't ask that.
I don't know actually what to ask, but this is the graph we got.
No, see, Abhishek, you have a different equation for climb. You showed earlier. Show me the equations which you showed earlier. No, even before. Next one. For climb, you have used something, no? Then for next one, you go. Next one. Okay, left side, left. You go back for climb. When you use this equation, you won't get the graph.
Yes, we got this graph.
You won't. Well, then no. What problem is? There is a G and all those stuff here. You have used a parameter called G.
No, sir.
Why not? If you're climbing, you have to use the G. Go through the book or ask your friends. Okay. You have to use if you have to use G. G is actually sine gamma, the climb angle. Okay. Sine of the climb angle gamma. Okay.
This formula is deduced from that only.
No. Where is the G here? This is for level straight flight without climb. Okay. So because already two percent are over, I don't want to go through the book and explain you. You go through the book. Okay.
Okay.
So that sine gamma you have to use. One more catch is there. Your climb rate you are telling us 25 meters per second. Correct?
Yes, sir.
When you use that, don't use the takeoff velocity because that won't be a takeoff velocity. takeoff velocity will be very low. So you will get, gamma is 90 or something like that, very near 90. Or probably, 55, 60, which is not really done. It can be, but I suggest you use a very high velocity so that the gamma value is below 30 degrees. My
Okay.
suggestion. Otherwise, you may have to recast the equations. The equations assume small gamma.
Okay.
Otherwise, you have to rederive using, not so small gamma and write it. But what I suggest is assume gamma is less than 30, but increase your climb speed so that V sin gamma is still 25.
Okay.
You go through that. When you go through that, you will realize what I am telling. Right now, you may not understand. Just note down what I am telling. Compare it with what you go through.
Okay.
If you have doubts, you can call me or ask me.
Yes.
Okay. 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 Anyone? Any other? Sanjay, you had
Yes.
a comment? Yeah.
Yes. Abhishek, have you plotted the graph for the landing phase?
We don't have landing phase.
You don't have.
Yeah. Yeah. If you look at their mission profile, they don't have. It's parachute recovery.
Okay. And yeah, in the design specification slide, you mentioned your CL max as 1.1. So is it not going to change for any phase or?
No, this is CL max. It will change.
Okay,
CL
so
max will not change. No, only
okay,
it can
so
change if you have
CM will
flaps.
change. This is CL max that we use.
okay. No sense
With
for
flaps or
normal
without?
setting for landing, it will change. So since they don't have landing, maybe.
Yeah. No, no. What I am worried is if you have flaps, you can still increase this. I don't
Yes.
know whether you plan to have flaps or not. It's
Yes.
better to have flaps because if you want to evade the missile or something, suddenly you want increase CL, it may be useful.
Okay.
For combat, good to have high CL max. But you don't have a combat phase, you just have to escape.
Okay.
Okay.
Thank you.
Okay. Thanks, Sanjay. You can put down your hand, Sanjay. Yeah. Any other question? Okay. If not, thank you,
Sir,
Abhishek.
excuse
Yeah.
me, sir.
Who's it?
Sir, if you
Ramdas.
allow me, can I answer Sanjeev's question? This is Renish, sir.
Who? Renish. Yeah, sure,
Yeah,
sure.
from the same.
Hmm.
Can you go to the constraint diagram? Sir, here the bottommost blue curve is for the climb. He has mistaken the vertical line as for climb, sir.
What is the vertical
Oh,
line
okay,
for
okay.
then?
That is for stall.
Mm. So
Colors
the
confusion.
acceleration,
Sorry.
no? The
Yes,
acceleration. Okay,
yes,
yeah.
sir.
Good. So the acceleration one, you take it for, n is equal to 5.
Okay. We have
Okay.
done that only, sir. For n equal to 5 only we have done.
Okay, good. But then
Yeah.
the climb we should take climb velocity is 25 meter per second. What G did you assume? That is capital G, sin gamma
Yes, sir. Uh,
for climb.
that I'm not sure exactly, sir.
Yeah. So there you look at your specification. The climb rate is 25 meter per second.
Yeah, yes, sir. I think we
Okay.
have taken V takeoff by
No, if
that.
you take V takeoff, what will happen? The climb angle will become very high.
Yeah,
Correct?
yes, sir. Yes, sir. Correct.
The climb angle is high. You can't really use those equations. They assume small
Oh,
gamma.
okay,
Then you
sir.
have to read the equations as not assuming small gamma, and then you do those equations.
Okay, sir.
Okay, that's a little bit more complicated. You can do that if you want. Hmm? Otherwise, the best thing is you say that when I say climb at maximum rate of climb, I increase my velocity,
Yes, sir.
which means that for when I want to climb at 25 meter per second, my total velocity is 100 meter per second. So my sin gamma is zero point 0.4. So gamma is what is sin inverse of 0.4? I'm not sure. Okay, sine 30 is 1 by 2 is 0.5, so it should be less than 30 degrees.
0.5.
Okay, yeah,
Yes,
yeah.
sir.
So less than 30 degrees is fine. You can use approximation and plot the graph. Okay, so the V you use in the weak equation should be 100 meter per second. The sine gamma you can use it as 0.4. Okay, then plot the graph. And in this diagram, we should show the feasible region also. Of course, obvious above the yellow line between this one. But for takeoff, the feasible is to the left or right. You have to see. And I asked you to give the red one, the blue one, the green one. Those things are not here. Okay, Renish. Hello, Renish. Abhishek.
Yes, sir. I understood.
Mm-hmm. Okay, okay. Okay, good. So, thank you, Abhishek. Next one will be Maritime Patrol Akshay Nivasini.
Can I present it, sir?
Just hold on for a second.
Okay.
Yes, you can start Akshay Nivasini.
Yeah. So good morning, everybody, and I'm Akshay Nivasani from Group 5, and I'll be presenting. I'll be summarizing the process behind our wing loading selection. So we mentioned our design specifications and also the data obtained from P3 Orion, our reference aircraft. This is our mission profile. Combat was chosen to be our primary mission, even though we have two separate mission profiles. And based on the primary mission profile, we have take I mean done our weight wing loading as well as weight estimation. And these are the data collected from our wing weight estimation. Okay, moving on. Wing loading effect on takeoff. The first segment was takeoff. Here we have substituted the takeoff parameter, that is the TOP, into the empirical estimate of the takeoff distance STO. Substituting, we derive this equation, and we've substituted our values into that, and we've gotten our graph. Here, as you can see, we've set our STO as 330 feet, and this data we got from our Jan Roscam, which is mentioned over here. So anything above the red line is our
Was
feasible
this
region.
STO given to you as in the specifications?
So we had to choose above that, and also we referred
No,
our
no, 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 no. When I gave the specifications,
no, sir, no, sir.
so don't mark it in red. You can mark it in green later.
Okay.
It is your own specification. You got from somewhere in the reference. Okay.
Yes, sir.
So draw it in green line.
Okay.
Okay. You can proceed. Thank you.
So we've fixed that STO to be 330 feet, and we've anything above the red line or the green line is a feasible region. Wing loading effect on climb, and we've assumed a stall velocity to be 200 kilometer per hour. This also was taken from the reference aircraft, and then it was we've chosen our rate of climb from the table 3.3, which was provided in Thomas E. Clark, and we've got our G to be 0.0381. We substituted again
How many engines did you have or you supposed to have?
2, sir.
Okay.
So then we substituted here. Again, we got a graph for the same thing. And even though our worst case scenario is a one engine failure, it still lies below the 500 feet per minute. So we've taken this region as our feasible region. Moving on to the wing loading effect on cruise.
When you did 100 feet per minute, did you take T by W as T by 2W in that equation? Yeah.
No.
Instead of, yeah, you have to do that because the curve, otherwise the curve will look different in that case.
Okay, we'll mail the changes.
Yeah. Instead of T by W, because one engine has failed, no?
Yes, sir.
So what is availability will be half the thruster.
Okay, sir.
So
We'll
instead
change
of
it
T
to
by W, yeah, you put T by 2W, but you plot T by W. Understand?
Oh, okay, sir.
Equation changes.
Oh, okay.
Here you put T by 2W and both inside the root and outside the root. But what you plot will be W by S versus T by W. You got me?
Oh, yes, sir.
Yeah. Then, it makes sense.
Okay.
Then climb gradient, you have to change to whatever is given there, 100 feet per minute. The climb G will change.
Okay, sir. We'll
Okay.
make the changes now.
It is not just changing one parameter to here. Okay, you have to change this also. That is why OEI, one engine inoperative.
Okay.
Okay, continue.
Moving on to the cruise. Our cruise altitude was fixed as 10 kilometers, and this was taken from our weight estimation. So we fixed it as 10 kilometers. And again, we've got this formula from Thomas E. Clark, where we substituted our V to be 500 to 700 meters per second. I'm sorry, there's an error over here. It is kilometers per hour. And this was also given in our design specification. So we got
Okay.
the graph. So we got a graph over here, and anything to the right of this.
I'm not seeing the graph. Probably you can unshare and share again. Sometimes, now I'm seeing.
Okay.
Okay. Yeah.
So
To the right of red. Okay.
yeah, we got our cruise velocity as 500 kilometers per hour, which was specified in the design specification. So we've taken that as the reference
To the
line
right is visible, left
to,
is visible.
to the right,
Okay.
because our maximum velocity is 700.
So give some indication in the graph. Just put a line there, arrow or something. That is the feasible region in all the graphs.
Okay, sir.
Just small things. These are not serious errors, but anyway.
So our wing loading on flight ceiling. Um, Again, the formula was taken from Thomas E. Clark, and we fixed the CL to be 1.2. There was a range given as in the Thomas E. Clark, so we took fixed it as 1.2.
So wait. So this during sealing, you don't fly at CL max. Okay, you reduce the CL.
Oh,
With your cruise or sailing height, you seldom fly near CL max unless you want to fly very slow.
uh, yeah, I think that we've done it in our graph over here. We've changed our height, altitude.
But CL, you can probably in that maximum at the maximum height, you will have only one speed, correct?
Yes.
And it won't be small and it won't be very large either. So you choose a CL which is slightly less. Say point up to 0.8. Wait, later you answer.
Okay.
After the presentation. Okay.
No, sir. I'm a group mate. Like, can I answer your
I
question?
know. Yeah, that's why. After
Okay.
this presentation, you answer. Continue working.
So as I said, we varied our height from 9 kilometers to 12 kilometers, and our feasible region will lie to the right of the deadline. For our acceleration, we've set our cruise altitude as 10 kilometers and density as 0.14. And again, V was given in the design specifications. So we're varying the load factor from 1 to 5. And here we fixed we've taken our load factor to be 2.5. And hence we got our.
This is not the graph you will get. It will be like climb graph. Okay. You got one for climb, no? The curved line in earlier one.
Yes, sir.
The graph will look like that. For various ends, it will look different. It won't be straight. Okay. So just check that out. You should use that equation.
Oh,
Okay.
but this is the equation that we substituted in, and
No.
I
Don't use this. Don't use this. Is not acceleration. You use actually, it means that it's moving at, it may be cruise. This is cruise actually. Instead of acceleration, you change the title to cruise. I'll accept this.
okay.
Yeah.
And moving on to our combat, it has two parts: the instantaneous turn rate and
Don't do this all this I told you. Only use the last one. Sustained turn rate. You have n, right?
yes, sir.
The top one is subsumed under this. Just say how much n is the maximum. The book can tell anything. I'm just telling you. Don't go about this. The n you calculate using the earlier one, right? The first one. Huh? You are
Okay,
given the maximum load. You assume a maximum n. Anyway, that load should be less than the maximum n only. So straight away use the sustained rate turn rate equation.
okay.
That is enough.
We actually
And
are trying
even
to change our turn rate.
no need. Yeah, you can do this later for your trade-off studies. For wing loading, it's not necessary. You do it for trade-off studies, it's fine.
Okay. So should I
So the rate you are telling, no? So the rate you are getting the curve. What is that?
no, sir.
The
This
rate.
was only our turn rate versus W by S, and this is for our sustained turn rate.
So you're varying the n,
Yeah.
this is what you should do for so if the acceleration is consumed under this, though you don't know what you showed earlier was not acceleration. Even
Okay.
acceleration you don't have to do separately. That maximum n is equal to 5 is there, no? 5 is not plotted here, no?
No, sir.
Plot
We
it for
we
5.
fixed it as 2.5, so we only varied.
No. Somebody told n is equal to 1 to 5, so you fix your maximum n. 2.5 is too less for a military transport. Slightly higher, at least more than 3 I guess.
Okay, sir. We'll make those changes also.
Right. And if it's not given in your specification, mark it as green, that constraint. You can change it later if you want.
Okay, sir.
Continue.
So to the last segment, our landing segment, again, we've taken the formula from Clark, and we fixed our value of CL was in the range of 1.8 to 3.
No,
And
here the CL max, this is correct. Don't say CL. Both are different things.
max.
CL and CL max are totally different things. Okay.
Okay.
The maximum value of CL is CL max. Yeah.
Then we substituted in our SL formula, and we've got this graph. Again, our CL max is fixed to be 2, and the region to the right is feasible.
Okay.
And we've plotted all the all these segments of the um, wing, wing loading constraint, and we've got the constraint analysis. And the region to the right of the yellow and the blue line will be our feasible region for selecting our.
What is the blue line, indicate?
It's a acceleration.
Okay, you
And
now combine it with that climb.
okay.
That n is equal to 5 is there, no? You combine it with that. Okay. Now, which one is red and which one is blue and orange, green and orange? You have to say. Does it reflect here? No. So I will know where you can make the compromise.
Okay.
Whatever you got from literature, you mark it green. Whatever is according to MIL specifications, MIL specification, you mark in orange. Whatever I gave you, you mark in red.
Okay.
Then we will be easy, where to make the first sacrifice or change. In case you're wing loading, it doesn't agree with, it is very unreasonable, you can do something about it. That's why I'm asking you to do that.
Okay, sir. We'll change it in the report.
Okay. That's it. See, the way to reference I already given you. The second one, airplane design part 8, John Rascam, it's not referred properly.
This was done for IEEE format, sir.
Oh, sorry. I thought you're
Okay.
only two references, no?
Yes, sir.
Then why Jan Roscam, J Roscam, two times the name is
Uh,
there?
no, sir. I made it easy for us to understand because TC Cork was
What you do is the line after two you remove. Then it
okay.
looks okay.
Okay. Sir.
Uh, okay, so that's it. Good. Next one. I mean, any questions? Yes, Sanjay, you wanted to tell something. You can tell now.
Yes, sir. Actually, in the acceleration, there is no T by W dependence on the equation, sir. So we get a vertical line. So like,
Acceleration? No. See, acceleration depends on n. Correct.
yes,
That
sir. Yes.
I'm not telling you to go. Whatever is there. Just
Okay.
one equation that climb with n is there. No.
Yes, sir.
Use that for your load factor. Acceleration is covered. Combat is covered. Inside combat, sustain turn.
Yes.
Turn rate. Everything is covered in that.
Yes. Yes. Yes.
Don't use anything else. You can leave the other things free. Okay.
Okay, sir. And also, sir, I think
Now,
by mistake she said our n is 2.5, maximum load factor is 5, sir. N max is
5.
5.
So just plot it for nmax is equal to 5.
Okay, okay.
You can plot for the other two to know where the upper side or downside is the feasible region. That's all.
Okay, okay, sir.
Now, Adarsh had a question. Adarsh, anything?
Yes, sir. Akshay, can you just go to the ceiling slide?
Slide or the
Yeah,
graph.
this one. So, what is this V? Is it the same as your cruise velocity, or is it different? Like,
Uh, the V
would
was
kind,
maximum cruise velocity, which is given to us in our
but
design specification.
okay, will it not be different for sealing conditions? Will it be the same V for cruise velocity? Like, you just substitute the cruise velocity for sealing, or will it be less or more? I'm not sure whether it will be the same.
I think it will remain the same because we're not.
No, Adarsh
Because
has a point. See, Adarsh has a point, Srinivasni. It won't be the same. You just, you look into it carefully. Good
as per,
observation, Adarsh. Yeah.
so as per the flight envelope, it will be more, I guess. So just plot
Yeah.
it.
It may be more, it may be
Maybe
between
less.
less also. We
Less
don't know.
also, yeah, yes, sir, yes.
Yeah, that's
Anyway,
why we varied our height from 11 to thing. But
no,
I
no,
think
no, no. The height area is different. What he's telling is the velocity at that height. V, you have to assume, no.
yeah, it will
That V
decrease.
will
So
be different from the cruise velocity.
So that is what my point.
Yeah. Good observation. See, but then CL also will be different. Okay, Srinivasni.
yes, sir. We'll change
Because
this.
your weight is equal to half rho v squared as CL.
Yes.
So W by S is QCL you want. Now both Q and CL if they change W by S can change. There is one more way which you can fiddle with. If
Okay.
if that is the blocking factor, you can use that. CL at high velocity will be very low. CL at low velocity will be very high. Correct?
Yes, sir.
So that is why I told at this side Q is very high. So CL will be very low. Okay. Now, okay. Only two more questions allowed. First from Rajeshri, then from Ramnathan.
Yes. Can you go
Raj.
to the final constraint diagram slide? Yeah.
Rajeshri,
What did
what's
you
your
say?
roll number?
Roll number 30.
Okay. Go ahead.
Can you tell me which is the feasible region you've chosen?
It actually changes because our acceleration is not there, and I mean we have to change that, and our CL max also changes. So previously it was this region.
Okay. Shouldn't it be to the left because your ceiling will give you the maximum? The region to the left of ceiling is what you should take, right? Because if you go to the right, then it means you cannot attain that ceiling altitude, right?
No,
Because
if
the
you go to
density will
the
be higher.
yeah,
If you move to the right, then the density will be higher because of the higher wing loading, which means you won't be able to attain that lesser density altitude, right? So shouldn't it be to the left? The feasible region?
Here it's actually 11 kilometers, and if you go to the left side, it'll become 12. So we can't go above our, our ceiling height.
No, Akshay Nivasni. See, the logic is if you have a ceiling which is more than what is allowed, it's fine. If you have a ceiling which is less than what is necessary, then you are not achieving your target. Understand? That's what she's trying to say. Akshay Nivasni, am I
Yeah.
making sense?
So we actually discussed on this, but then
Hmm.
we concluded it was to this side. So
But
I'm not
then
sure.
reason out. It's okay, discussed. But then, if you make a mistake, we have to correct ourselves. All of us make mistakes during design. Design is not a perfect science. So when we make, we correct ourselves. That's it. So don't you think this is correct? If you have less density and you can fly, more than what ceiling you have, that's okay with you. But if you can fly only at a ceiling which is less than what is prescribed, that is not what you want. It's not the feasible region. Does it make sense?
Yeah, I think.
Yeah. So I think this is better. This is correct. Yeah. Ramnathan, last question.
Sir, yes. Sir, for finding
No, not
ceiling
sir.
condition,
Akshay Nivasini.
uh,
Sir is not at all in the picture. He is just only a moderator.
okay. So I
He is
have
the
this
boss today.
general.
Yeah.
So I'll ask Akshay, sir. No problem.
Mm-hmm.
So
Yeah.
for finding ceiling conditions, we don't know CL, we don't know height, and we don't know the speed at which you are flying at the ceiling condition. So with these three unknown parameters, how can we come to a conclusion that okay, this is our ceiling and ceiling is
Uh,
ceiling given?
yeah, we sir had given it in our design specifications, and I mentioned it in the first slide itself. So
Okay,
we
so
got a
now
height
okay,
and
okay.
our speed
So
also.
okay, so you're taking your cruise speed to be the ceiling. I mean the speed at ceiling.
Yeah, but now because other said it varies and it might vary, right?
Okay, okay, okay. But again, you have two parameters, right? One is the speed and one is the CL.
Yeah. I'm
Uh,
sorry.
So for a
Answer to Ranganathan's questions.
wait. No, not yet. Let Akshay Nivasni answer.
So from what I understood, he said we had three unknowns, and we have
Where three?
two.
What are the three unknowns?
Um, he was talking about the velocity and the height,
Hmm. Hmm.
and also like CL. Now we
Height
have
is known. No, height is
yeah,
given to
height
you.
is known, and also speed
Hmm.
was given to us.
What is unknown is wing loading also.
Yeah,
Yeah.
Speed at ceiling is given.
yeah,
Actually
cruise.
given assumed.
Yeah,
Is it given? No, it is assumed. So now his question is, how do you make those assumptions? The combinations of V and CL.
no,
I
sir.
think that is the question. Am I
Our
right,
cruise.
Ramnathan?
Yes, sir. Yes, sir.
Yeah,
Because when I was finding for my ceiling condition, I couldn't
yeah.
come to them.
Yeah.
Our cruise speed was given to be 500 kilometers per hour. So we took that as our velocity.
I will
Okay,
tell you a
okay.
secret, but it should be not be the cruise velocity. Okay,
Okay.
I will tell you a small secret. Anything reasonable is okay because we don't know really. Okay, Ramnathan.
Yes, sir. Yes, sir.
Yeah, you don't know either get it from comparison abstract if it is there. Most
Yes.
probably you won't get it there in all probability. So anything reasonable is okay, but it shouldn't be. It should be logical. That's where I can test your understanding of the, your problem. I can check whether, for example, at high speed you have high CL like this. Then I think it is wrong. But if you have a higher speed and lower CL, yes, I think it's correct. So
Yes.
Akshay is asking, this is where you can fiddle with. Okay, you can actually, choose the speeds right now at this point. Later, after you design, it will be fixed. You will find out what is happening.
Okay, sir.
Okay. Okay,
Uh,
good. Good.
Sir, it's like we have the same Mach number, sir. So like we are going to
uh,
fly the ceiling with the same Mach number. So m
uh,
into root gamma RT. So that T will change because of the high altitude, and so
Fantastic.
this T will change. Like
Okay,
it's
good. But
not the same way at the like no, we are not flying at the ceiling with the cruise
you use
velocity.
less logic. It's not a foolproof logic, but you use that logic. That's okay. Because no logic is foolproof here.
Yes.
So now the
And it's
CL.
not
CL which
real.
you assume there will be different.
Yeah. Oh yes, sir. Yes.
Yeah. Because the
Sir, and
stall
our
velocity there will
objective
be
must be
different. Hmm.
our
Your
objective
objective must.
must be whatever CL we use now, we have to
Hmm.
obtain during the wing selection.
No, no, no. This is just to get an idea of the estimate. When you fly, the wing loading keeps changing. So you are just getting an idea. You are still,
What wing loading, sir?
you are.
Now, if suppose we are assuming some CL around 2,
Yes. Why are you assuming that CL to find the wing loading?
yes, sir, yes, sir.
So
So we
what's
have,
happening? So this wing loading is something for you to work with and get up with the initial, idea. So if you don't get the same thing later, it's fine. As long as it flies, finally you check your performance and see where it meets the requirements after you design everything. Okay.
yes, sir,
So then you say, okay, you heard that famous proverb in Tamil,
sir, uh,
"Pullayar udikke poi korangana kada."
sir, no, sir, no, sir.
Okay, anyway, for those who don't know Tamil, I'll explain in English. They basically say that, during this Ganesh Chaturthi in ancient days, we are is going to come in next few months. So we'll actually, we'll take the clay and make it out of our own hands. That's the way it should be done. Not, coloring everything, polluting the environment. It's not the usually done thing. That's a later development, I think. Usually, in India, we'll take the clay, bake it out with our own hands on the same day, perform the puja, and then after that, we will, we will go back to nature. So, what mix it with water and pour it into some tree or something. Okay, so that the sand goes back to nature. That's all. So now, for this purpose, people will go to some place where the clay is available. They'll go to river banks or lakes or some small ponds so that you get that mud. Now, when you dig that mud, okay, you wanted to make Ganesh ideal for Playar in Tamil. But finally, after you finished, you got a monkey instead. Okay, so aircraft design is something like that. You want to make something like you wanted that Ganesh in idea, but you craft it initially. Take the clay, roll it, do something. Finally, when you look at it, you don't get the shape you want. You might have got a monkey. Aero design, the first round of these, this, what do you call this? The first design, conceptual design. It's like that. So if you don't get that same thing, you come back and start again.
Yes, sir, yes.
So here we are dealing with the initial phase of that. We are still the
Yes,
clay is not formed yet into perfect, parts and all those stuff. Okay, Ramanathan.
yes,
I'm sorry for my similes. It may not be very perfect, but I hope the message went across. Okay. Yeah. Now, do we have time? No. Time up, right?
Yes, sir. Time.
Okay. Sibi, you want to say something? No more questions.
Sir,
Yeah.
like
Sir,
Hmm.
about the like a presentation, sir. Like, can I ask one more question, sir? No,
No,
like it's simple,
no, no.
simple
But
question.
you can. Simple. Okay.
Okay, sir. Sir, like
Hmm.
so in their constraint diagram, they shows their
Ask them.
feasible area. Okay,
Ask
so
them. Ask them. Ask them.
okay, so Akshaya, so for your constraint diagram, you choose your feasible area to the right side of landing constraint. So how do you choose it? Like your landing constraint should your feasible
Go
area
to
should be left
show the
side to the
landing
landing
constraint,
constraint.
Akshaya.
Yeah.
So like your landing constraint should be left side to the feasible. Sorry. Landing constraint. Yeah, feasible area should be left side to the landing constraint, but like you have chosen that it is the right side. Why
Where
do
did
you,
she choose?
sir? Like
Did it
where
choose?
in
Did it
the
choose the
they told that,
constraint?
sir.
Go to the constraint diagram. Hmm.
So, like it's around 2000, sir, for landing, but
Hmm.
they chose it in the right side. So like it is.
Can you
It
explain
could
why it
actually
should be the left side, CV?
sir,
Explain it to
like
Akshaya later. Now we are out of time. Okay.
okay,
Explain it to the group. Hmm? At a later, you can contact later. You will be late for next class.
okay.
What do you have in next class?
Flight dynamics.
Dynamics.
Like
Model.
that. Okay. So I don't want you to be delayed for that. We'll
We
stop
don't
here
have
now. Hmm? I think. What is it? We don't.
like we don't have flight dynamics class next time. It's
Why?
cancelled.
Why?
Like, I don't know, sir had some other commitments, so we cancelled it.
Fantastic. So we meet again at 9:50. We'll have aero design class. Or shall we have CFD? What do you want? It is your choice. Don't I won't let it to Sanjeev. I will let the choice rest with Akshay Nivasini, who is the boss now. Akshay Nivasini, you want CFD next class or you want aero design to continue?
Safety.
CFD. Okay. We'll have CFD then. Second half. We'll meet at 9:50. Probably I may take a little bit more time, but we'll meet. Okay. Thank you. Thanks. Bye then.
Thanks.
Thank you. Bye. So have you taken attendance? No. Take it.